Okay, so before you do the projector, we quickly talk about actually you can prove the formulas for the subtransient indulgence or transient indulgence by assuming the range of frequency of the dynamic. For the subtransient dynamic, we assume the frequency will be very high. So you can just give S a very large value, close to infinite. But when you study the steady state dynamic, you can give S 0. And for the transient dynamic, you can give some value between the infinite and 0. So that will give you, that will make some of the factor in this formula be bigger than the other. So you can somehow ignore an important one. Then you can get the conclusion. So for that transfer function, so it will take a value under steady state as constant LD. For subtransient dynamic, it will have this value. And for transient dynamic, it will have this value. And if you plug in the formulas from the previous slide in that table, okay, you plug in the formula, for instance, here, so you can find those formula and plug in the formula, you will prove the formula on the left-hand side in the table. Okay, all right. So that will be match exactly the formula there. But this table does explain those formulas are called classical expression, not the most accurate one. If you want to keep everything without ignoring any resistance to figure out the time constant, you can have more accurate formula. But those ones are not important to us. What I said at the beginning is I strongly recommend everyone to pick anyone to prove. Like I put it to the appendix. In the past, I just go through this step to prove. For example, let's just prove LD double prime. We start from those three flux linkage equations. Only those three equations are related to the LD double prime. I can ignore other equations. So from those three equations, I'm just assuming the flux linkage in D will be proportional to the current change. So this one will represent the equivalent indulgence, right? This is accurate formula that talk about how the flux linkage is going to change. But right now, we introduce LD double prime, so that flux linkage is supposed to be proportional to the change of the current in the DSCs, and that coefficient will be LD double prime. So the next step will be, we will need to eliminate any currents that are not related. Like for instance, we want to eliminate LD and LF with damper 1D and field 1D current. So you will, this step is pretty simple. You just, the three equations, and using those three equations, you eliminate two of the three variables. So finally, you will get this one. Okay, this is still slightly different from the formula in that expression, but if you introduce the each indulgence or mutual sub-indulgence based on how we define, you will get exactly the same expression. So for instance, for this case, we assume MR is equal to LAD. So you'll get exactly that formula. Okay, so this part is related to the parallel connections considering the three branches, LAD, L1D, and LFD. Now, if we do some simplification, so this one will give you exactly that parallel. If you're sensitive enough to this expression really means this one, that one, and those three indulgences connected in parallel. Okay, so those in parallel then connected with this liquid indulgence in series. If you're sensitive enough to this expression, there's some other textbook. They are a little bit hesitate to assume those two to be same. Okay, they try a compromise. They assume those two are not same, but why not we assume those two to be same? I don't bother to explain why this equation is more accurate than that equation. And later I'll tell you that's not important at all. Once we derive the final model we can use for stability study, either you follow this assumption to make this one be 0, or you make the two product to be same. It doesn't change too much. But if you make this one, you will see another different formula, which is this one. So why do they like this formula? Because all the inductances in D or Q with single double prime will follow exactly the same pattern. That's why they like it. Okay, so later when we derive circuit, this one is more convenient. That make the model more simpler. So later we might try this one, but I'm just explaining. So if you give the circuit some the typical value, try to compare the LD double prime calculated by using this method by assuming the MR is equal to LD. Or you try this one by assuming those two parts are same, the value are very close. Close enough, and the difference is not important at all to at least to power system stability study. Similarly, this another just try to prove this formula, and you see you somehow know why they lack this expression, because this match this structure very well. Okay, this one with either assumption, because this one doesn't involve damper winding. Okay, so either assumption doesn't change this expression. So they somehow try to make anything like LD prime, LD single prime, double prime, MQ, single double to take the exactly same structure. So later they can utilize this structure to make a derivation simpler. Okay. Yeah, I strongly recommend everyone that pick anyone, try to go through this process to prove it. Maybe you can try I already show you the LD single prime, double prime. You can try some maybe LQ, or you want to try LD0 single double prime. Okay, this is the slides we just work on. I already explained why this order has to be true, because this inductance compared to that one, this one will add another parallel branch here. So that has to make this parallel inductance be smaller. So this one must be smaller than that one, and anything else will be same. So this one has to be smaller than so without the zero time constant will be smaller than with zero time constant. And sub-transient time constant much smaller. And also the one with zero will be bigger than the one without zero. Okay, because it also add the difference only just add another parallel inductance, which is the leakage inductance. Anything else will be same. So similarly, you can also show the ordering. The time constant with zero is bigger, and the sub-transient dynamic time constant will be much smaller. For the inductance, so if you assume this one, so the structure will be LL plus LAD. Then you add another parallel to LAD. Then you add the third one to the LAD. Okay, if you like this structure, but to spell out the formula for this parallel inductance, that will be very complicated, right? You don't like that one in your equation. So that's why some others like this way. By assuming this one to be true, so they will take the exactly same structure as this one. This is more convenient to derive the later formulas. So you have to order those one. As I show, LD is the largest one, and this one is second, and this is the third one. Because by moving from without prime to prime parameters, from single prime to double prime, you keep adding the another branch to be in parallel with the LAD. So you will make the total L be smaller. So this is same. You see, even the in the QSs, they take the exactly same structure. So which means if they do any proof involving this structure, they only do once, right? They can copy the same thing to the other circuit. So that's why they like this one. Any question? This table just confirm those ordering. If you give them typical value for the cylindrical rotor generators, such as the hydraulic units, or round rotor generator for the thermal unit, usually the values of those X or L or time constant fall into those ranges. This table is very useful if you want to make up some data. For instance, you get some power system model with all the very low order model, classic model, but you want to make generator to present more interesting dynamic. You want to add like sub-transient dynamic or transient dynamic, but you miss those data. Okay, so if you have very classic model, very likely you may have this one or maybe that one, but based on this range, you can also create the SQ or S double prime or T double prime. Also, for instance, if you have round rotor generator, you also want to add some like hydro power plant. Like you have a power system model, every generator is like a thermal unit, which is round rotor generator, but you also want to assume one region to be a hydro power plant. You definitely cannot use thermal unit. You need to change it to hydraulic unit. So when you change to hydraulic unit, you can use this table to create another set of data, because the DSs and QSs are not fully symmetric anymore. Anything else? Let me see. Okay, so next, let's talk about why this one is very important. Because this is, if you question how can I get those parameters, one answer could be the manufacturer may give you initial parameter for those values, right? Before they sell this generator to you, this unit to you, they may do some internal tests and then give you some plate value or some detailed test value. So you can definitely use those values for your simulation study. But there could be some two concerns. The first one is when they do such testing, they put in their test bed. That doesn't represent how the generator behave in a real power system. Actually, the same IBR, that same problem also is true for a lot of renewable generators, such as solar farm or wind farm. When they give you the model is only accurate for very small systems. They set up very small environment to test the parameter. But when you connect to large grid, some parameter need to be identified again. You have to do like what we call model validation. So you definitely, even they gave you those initial value for those time constant, you still may want to do your test, right, to verify or validate those parameters. And also when you use the generator for long enough time, some parameter will shift, will maybe float from to some other values because of aging effect, because of different operating environment. You still want to do testing. So this slide is going to show how you can estimate those values from a frequency response test using the exactly same idea we show on that whiteboard, okay? Just by injecting the signal at different frequency and measure apparent inductance from the terminal. And that one will be the value of that this transfer function at that frequency. Then you can draw, in the frequency domain, you can draw some chart to indicate how the LD will change with frequency, which is called a ball diagram. The ball diagram is a tool, very useful tool to show how the transfer function is categorized. So we already know this ordering, right? So which means if we consider the reciprocal of each one, so that will be opposite. So this one will be smallest one, and that one will be largest one. And each of those one will be either poles or zeros of this transfer function. So when you, does everyone know how to draw the ball diagram? BOD, ball diagram, right? Ball diagram is a diagram accurately categorizing what this transfer function is. There's a one diagram about the magnitude, one diagram about the phase. So basically just this transfer function, it takes complex value. It can have magnitude, absolute value, and also phase. By plugging different s, which is complex number, you can get different magnitude and phase. Okay, so this is what the ball diagram may look like. So S is actually the frequency. When you inject different signal at different frequency, you start from 0, which means it's just steady state condition. Steady state condition, like you just let each S be 0, then the value has to be LD. So at a steady state, it has to start from LD. Okay, then you gradually increase the frequency until some value, okay, bigger or close to this one, the smallest one. Then you will see the slope will become around -20 dB per decade. Okay, so this indicates there's going to be a pole, which is this one. So the transfer function first experience a pole, and which has the smallest value, the frequency value, and then when you increase frequency, the next one will be 1 over TD single prime, which will be this one, which is on the numerator, which means it will add a positive 20 dB per decade. We'll cancel this slope. So make slope back to 0 again. The next one will be a TD 0 double prime will go down as -20 slope and then become flat again. Okay, so if you're able to draw this figure, and by finding the turning point, and you actually can identify those frequency, then you calculate the reciprocal. That will tell you the time constant. That's exactly how they do it, right? But real Bode diagram or Bode plot is not as ideal as this one. It will be very smooth. Then you have to utilize the other plot on the face. The other plot face says when you have introduced any pole, the angle will decrease by 90 degrees. Okay, when you add 0, it will increase by 90 degrees. So you can utilize those phase plot to help you to identify where the real turning point is. So let's assume some typical value. Okay, here you can use MATLAB to draw the Bode diagram. So this is a magnitude diagram. This is a phase diagram. So magnitude diagram is not like coming from 0 and suddenly change to -20, but it will go through some process. You have to somehow pick a point at the center, or you can have another way to do it. For example, this is what I assume I already know those values. You draw the Bode diagram. What if you don't know those values? You can just assume some value. By assuming some value, you can draw the Bode diagram and try to match with this one, whichever match this one best. So you can just program a very simple code, right, to find the best match. Then that one will tell you the time constant. This is not a complex problem. It's very simple, very easy engineering problem. Does everyone follow? Okay. Yeah. So anyway, what I'm saying is, if you present this plot to someone, that can accurately identify those time constant values, right? That's not a big problem at all. Okay, next we want to talk about another differential equation for generator, which is the so-called swing equation, or swing equations depend on first order differential equation or second order differential equation, whichever you consider. Okay. So swing equations come from the Newton's second law. The Newton's second law says if you give some turning, maybe a revolutional mass, some torque, some net torque, it will accelerate. Okay, the acceleration is proportional to the net torque you gave, and the coefficient will be the moment of inertia. So that is called a revolutional motion. But if you're talking about like linear motion, that's similar. So if you give it a force, if some object is subjected to a net force, the net force will be proportional to the acceleration, okay, linear acceleration, and the coefficient will be the mass or inertia. So here, this is just from the second Newton's law, and J is the moment of inertia of the generator, and omega m is angular velocity, which represent the actual revolution, the speed of the rotor. And TA is called accelerating torque, which is equal to the mechanical torque from the turbine and the electric torque from electromagnetic torque going to the grid, going to the network. So for the convenience of the representation of the swing equation, usually we want to introduce inertia constant for the generator. So inertia constant has a unit of second, which is defined to be the kinetic energy of the generator when it's operated as a nominal condition divided by the base power, three-phase base power. Okay, because you divide energy by power, so the unit will be second. So the H here will means it's similar to some time constant, even it's not accurately presenting the time constant of swing equation, but it will have somehow showing how large the time constant is for the generator. From this definition, you can calculate the moment of inertia of the generator using this H factor, this inertia constant, and also the power base. For thermal unit, which typically round rotor generator, the time constant can be smaller. If it's a 2-pole and bigger for 4 poles. And for hydraulic unit, which is cylinder pole rotor generator, and time constant can be 2 to 4 seconds. Okay. In some textbook, they also define another inertial constant, which is equal to a double H. The physical meaning of double H can be better explained compared to inertial constant, because this double H is called mechanical starting time, which means if the generator starts from an off condition and you inject, if you're able to inject a rated torque to speed up from 0 speed to the signal speed, that's how much time it will going to take, right? And you can easily explain why this one is a double H, because H is defined to be the total kinetic energy. Kinetic energy is defined to be half of the moment of inertia multiplied by speed squared. That's the definition of kinetic energy. That's energy revolving at the signal speed, and divided by the nominal power. That's the H factor. Okay, but if you start the unit from 0 speed to the signal speed, it will take a double time. Why? Because speed is not suddenly happen when you turn on the unit. It will linearly increase from 0 to that value. So the time will be double. Okay. Which is like you try to count the time by assuming the energy to be a rectangular area. By using the rectangular area for the energy divided by the power, that gives you the time. But actually, the speed increases linearly. It's another area of a triangular area. So that would, the triangular has to be have double length on one edge to give you the same area. So this time will be doubled. Then we can utilize the inertial constant to redraw or rewrite the equation. So we just replace the J by definition using the H, the signal speed, and also the rated power. And so we want to derive the per unit value. So we can use one of the omega 0m divide the omega m. So that will create per unit value here, and the remaining part will move over to the right-hand side. Okay, so we can define, if you go back to the early slides on the per unit values, and this is exactly the base of torque. So you will have this line, and this line tell you I can change the formula to the same formula in per unit. Okay, except for H. So here omega R is in per unit, and each T is in per unit, and T is still in second, and H is in second. So those 2 seconds will cancel. So that make both sides will be in per unit. Okay, so here the per unit speed can be calculated by the mechanical speed divided by the signal speed, signal mechanical speed, or you can consider the number of poles you can transfer to the electric speed. For the electric speed, this one will be 377 for 60 Hertz, and this is actual speed. So next step, you can add another thing, because here you only assume all the mechanical power or torque is utilized to drive the rest of the power system, but you can add another loss, which is due to the maybe the damping torque. Okay, so this one usually assumed to be a speed deviation dependent. So which means you operate exactly as 60 hertz, you don't have much on this damping torque. But if it deviates from the 60 hertz, so this one will increase. This one can somehow give you the damping effect, which it behave like a friction. We'll talk about what this one come from in the low modeling part. So this one, even we call it a damping torque because it's the physical mean is a type of torque, right? It will take part of the mechanical torque, but it's not completely coming from the damper winding of the generator. It can also come from a frequency dependent load. So this one, because it will take part of the mechanical torque or power, so it will behave like a load. If your system has any load which is depending on the frequency deviation, so that can add value to here. All right, so the next we want to dig into this equation about the relationship between the rotor angle and the speed. We know the rotor angle is defined as the Q axis relative to the synchronous frequency, synchronous frame operating at a synchronous frequency. Okay, so here we use omega 0 to indicate that synchronous frequency. It can be 60 hertz, right? For 60 hertz, that will be 377 radian per second. And omega r is the actual rotor speed. So if this one is exactly omega 0, the angle doesn't change. So it may depend on what is the initial angle you assume. Like in the early slides, we assume the signal generator operate at some that we define time equals 0 when the magnetic axis is same as the axis of A, right? But in reality, how do you know? But that's not important. Let's just assume that delta will be indicate the relative position to the reference frame. But if the rotor has speed higher than signal speed, this delta will increase, other will decrease. So this equation will be true. Okay. Then the next one, we want to change both sides to be in per unit. So we divide both sides by omega 0. So that will give you a per unit value of frequency deviation. So delta omega r is how much omega r deviate from omega 0 and normalize based on the synchronous frequency. Then we bring this equation from the previous slides. So those two equations will be the so-called the swing equations, which are two first order differential equations. Okay, so this is the most used equation in the stability study. Based on those two equations, you can draw this this block diagram. The block diagram will tell so Tm minus the Te, that will be the accelerating torque. The accelerating torque goes through the damping torque and also to change the speed. That can be categorized by this block, this first order block, and then that will give you the speed deviation. The speed deviation can be translated to how the angle will change. We'll go through another integral component. Okay, based on this block, now you know why h is not time constant. H is a inertia constant. Inertia constant, which means it can categorize how much inertia the rotor has. But in this equation, it's not a constant. Constant defined to be what is a true constant, time constant for this case. For this first order system, what is the time constant? Time constant has to be in the denominator will have be Ts plus 1, right? So it'll be 2h divided by kd. That will be a time constant. So if a kd is 0 or very small, the time constant can be very large. If kd is very large, and time constant can be small. Okay. So in the frequency regulation session, we'll know why this one can influence the frequency performance, because that influences how quickly the frequency can recover. By adding governor, you actually can influence this part to make a frequency response quicker to the disturbance. Okay. The next one is if I calculate derivative of the first equation, I can get second order derivative of delta. So that will be the first order derivative of speed deviation or speed. Then I can make both sides to be per unit by dividing both sides by omega 0. I can get the third equation. So why do I want to get third equation? Because I want to replace omega by only using delta. So if you plug in the delta omega bar here, so this part will become first order derivative of a delta. And this part can be replaced by second order derivative of delta. So you will get single second order differential equation only about root angle. Okay, so this is single equation is equivalent to the two equations. So you can call this one to be like swing equations, which mean two single first order single equations, or it can be just single equation of second order. Okay. Okay. Any question? All right, let's move on. All right, so next step is very critical. So we're going to connect the swing equations with the earlier differential equation from our model about either flux linkage or current or voltage. So far we have modeled all critical dynamics of a seamless generator or seamless machine. We have a swing equation, we have flux linkage equations. And if we put all the equations together and identify which one can be differentiable, which means in the equation, you will see a derivative of that variable. So that variable can be either just voltage, current, or flux linkage, or the angle, or speed, any of those. Then I just put all those variables in one column as state vector. So that will be the state vectors of my model, okay? And how many time constants do we have? We have like T single prime, T double prime in DOQ, considering like short circuit or open circuit disturbances. We also have inertia inertia constant, not time constant, but 2H. Somehow also represent some time constant. And there are also some other parameter like we have a lot of inductance parameters or resistance parameters. And in the swing equation, we also have mechanical torque and electric torque, okay? So how can we integrate all those equations, variables, and parameters into the same set of model? If we use ceiling pole machine as one example, for ceiling pole machine, we have 5 windings. We have for the stator, we have a D and Q. And for rotor, we have 1F and 1D and 1Q. Okay, which means each state vector will have 6 elements. In this case, we also consider 0 sequence. Okay, for balance condition, you can take away the first row, then you only have 5 elements in each vector. Okay. Then if the flux equation or voltage equation will be given here. So here you see the equation assume the state vector to be about current. So you take this vector as state vector. But actually, you can also let flux linkage to be the state vector, right? Because flux linkage is proportional to current. You can plug in this second equation to the first equation, and you will have only derivatives about flux linkage. So that's up to you, depending on which one you prefer to model. So let's assume we focus on flux linkage. So both equations by plugging how the derivative of current change with the derivative of flux linkage will have this new differential equation. We also have swing equation, which introduce two equations. So for this TE, we know the TE electric torque is actually proportional to the, if you can utilize flux linkage current, that can be calculated by this atom in the parentheses, okay? And this one is also connected to the flux linkage here. So you actually can put all the equations together. That will give you first model if we're talking about the state space representation. So now we have state vector with all the utilized flux linkage plus omega and delta. We'll have the first state space model, which will be written in such way. Okay, the vector will be everything that is differentiable here, because we focus on the flux linkage. So it will be flux linkage, speed, and angle. Only three types of variable. And f means it can be nonlinear function. We just integrate all the equation here, and in this function, x is state vector. Okay, EFD is actually the field voltage. So if you don't change the field voltage, this one will be constant. If you have exciter to increase field voltage, this EFD will be changing value. Tm is from the turbine. So if the turbine opening is not changed, Tm will be constant. Okay, ED and EQ will together. This ED will be the real part of terminal voltage. EQ will be imaginary part. So they together determine a voltage phasor at the terminal bus of generator. Okay, so this voltage will change with the grade. If you have a disturbance in the power grid close to this terminal, that will decrease this voltage. So now you see we can treat EFD and TM as input from the exciter and the governor of the generator. And the ED and the EQ also as input from the grid. But if you can also add the power flow equation, that power flow equation will tell you how the ED and EQ can change. So you can add the power flow equation. So power flow equation is not differential equation, it's an algebraic equation. So finally, you are going to have a set of differential algebraic equations. That is usually how a power grid is modeled. Okay, the differential part is mainly from the generator, like flux linkage and speed and angle. And it can also from exciter. If your exciter also has some state variable, or a governor, if a governor has some state variable, okay. Definitely later we're going to also model load. If the load is dynamic load, that can also add some state variable. And also we have a power network on the power flow that will give you the algebraic equation. So eventually we'll have DAE model for the power grid. Okay, our next job is going to derive this model, a very detailed this model to show every equation. Okay, then we'll gradually simplify the model. Let me finish this slide. Okay, I gave you what I'm going to do in the next maybe in the next lecture. So if you include all the equations about all the state variable, you'll have the most accurate model. I don't bother writing down all the equation, but you can do it on a piece of paper. But I'm telling you, if you do that for Sealing pole rotor generator, the state vector will have 7 state variables. So it's like a 7-dimensional state space for just single generator. Okay, 2 generator, you just multiply this one by 2. Round rotor generator, that will add another damper winding. So we'll make this one be 8-dimensional. Okay, this is the most accurate model we have. Then the next step, this one represents the test, because in this model, there are 2 flux linkage for the stator. There's a side D and a side Q. But in those circuits, we know for steady state condition, which is equivalent to I do short circuit between those 2 points. Because this is actually the major source changing the power output from the generator. Not those stuff. Those stuff only determine dynamic in transient or subtransient dynamic. Similarly, under steady state condition, those two will be directly connected. So those won't influence much on the power output. Okay, then we can do a test. We just add a disturbance at terminal of generator, and we compare two models. The first model, we model everything. The second, we just simply treat the P psi for the stator flux linkage to be 0. We just cross off this psi d and the psi q, not from the whole equation, only from the differential part. Okay, so we don't treat psi d, psi q as state variable. They can change, but they only just influence the algebraic part. They are not considered as state variables. So there's a two tests. One simulation is with detailed model like 7D or 8D. The other is ignore the psi d and the psi q from the two model. So they match pretty good. Only after, this is like 0.3 second. Beyond 0.3 of 0.4 second, their difference can be almost ignored. They only show, you see the ripples at the beginning, that's only within 0.1 second. Okay, unless you really want to study this dynamic, then you definitely need to consider this one. Otherwise, just treat it with 0. That largely reduce dimension by 2. Okay, any future models we're going to derive, you can see from book, they usually assume the psi d, psi q to be 0 for the stator winding. So let's just simply assume the psi d, psi q to be constant. Then that reduced dimension by 2. Okay, for cylindrical rotor generator, we only have 5 state variable. And this model, if you see any differential equation using only those 5 state variable, 3 flux linkage and 2 from swing equation, that is called 2.1 model. That's so-called 2.1 model. 2 means you have a 2 in the d axis and 1 in the q axis. And 3 equation, 2 variable you cannot ignore. So those will be there anyway. Okay, this one is called 2.1 model. There's also some model, they call it a 2.2 model. When those two numbers are equal, you know that's a round rotor generator. So 2.1 model, 2.2 models are the most accurate model you can see from any stability study. Okay, nobody use any model like 7D or 8D model. They usually, if you want to make a generator be very accurate, usually 2.1, 2.2 are the most accurate model you can deal with, even with power industry. Okay. So in such model, there's some time constant like inertia, transient, and subtransient. Next one, you can eliminate the subtransient dynamics, which means in the state vector, you can ignore maybe the damper winding in each axis, or the round rotor, you also ignore the damper winding each axis. So now you will, for the cylindrical rotor generator, you only have just flux linkage of the field winding together with omega and delta. Okay, you remove those two. And for round rotor generator, you keep flux linkage in each winding. Just make the symmetry for the between D and Q. So you have a psi FD plus psi 1Q, but you ignore psi 1D and psi 2Q. Just make it simpler. So you will generate 1.0 model and 1.1 model. And 1.10 model is also called one-axis model. So if you read any paper written by control people, someone from outside of power engineering, this is the most complex model they're going to use. Okay, so because they are a little bit hesitant to use only swing equation. If they use swing equation, you will say, okay, that's not good. They will add this one. They don't bother adding like damper winding because that's too complex to figure out. So third order model may be good if you want to write a paper to present to control people, someone from outside. This is good. This is good enough. Okay. But actually, unfortunately, in reality, most generator are round rotor generator. You definitely need to consider this model. That's 1.1 and 2-axis model. So 2-axis model is very popular model for power system people if you don't want bother to study 2.2 model. Okay. All right. Finally, if you don't want to show any flux linkage, then you just like you forget almost everything before today's lecture. You only know swing equation. That's called 0.0. Okay, seems to be nothing, but you still have a delta omega or classic model. Okay, so usually to do research, you want to verify the idea, you can start from classic model, gradually maybe move to the 1.1. Yeah, if you then you submit the paper. If some reviewer asks you to verify with more detailed dynamic, you can consider maybe upgrade some generator to 2.2. Yeah, that's your process. You can consider generator model. Okay, so this is the last slides. Let's continue on Thursday.